Today's topic is the Rydberg equation and how we can use that to calculate the energy of photon emission. If we know the energy of photon emission, we can further use that to determine the wavelength of that photon at any region of the electromagnetic spectrum. Niels Bohr proposed a model for the hydrogen atom, and in that model he said that electrons can only exist at certain quantized energy levels. If we take a look at this model, we'll notice that there are these various shells, n equals 1, 2, 3, 4, 5. What Bohr was proposing is that electrons can be in any of these energy levels. If they get excited, they will jump up to higher energy levels, but they can't exist between those levels. They basically jump from one level to another. They can jump up if excited, and they can come back down as they relax. If an electron relaxes from a higher n level to a lower n level, we will have photon emission. And the photon emission can be in the visible light spectrum, such as you see here, or it can be in areas of the spectrum such as UV or infrared. Whatever the case is, we can figure it out by deploying this equation. The change in energy equals the Rydberg constant, 2.18 times 10 to the negative 18 joule, times 1 over the electron at its final level squared, minus 1 over the electron at its initial level squared. By the way, sometimes you will see this with no negative sign here. You'll see it with a positive sign, and then these two terms are flipped. You can use either one and it will get you to the same place. And the truth is, in the end, if we get a negative number, we simply take the absolute value of that number anyway, because we need a positive value for the next steps. So now that we have this under our belt, we can go on to consider the strategy that we're going to use to calculate the wavelength of light when we have one of these electronic transitions. Part of our strategy, as noted, is using this Rydberg equation. Again, we see that up here. We also need some other equations. We need to understand that the energy of a photon is equal to Planck's constant h times frequency. We find that equation right here. And then finally, we need to understand that the speed of light is equal to lambda, the wavelength, times the frequency. This is true for all electromagnetic radiation, and the speed of light is a constant. It's 3.0 times 10 to the 8 meters per second. So we're going to use this equation, and this equation in order to figure out a problem. Here is the Rydberg equation that we just looked at, and now we have a problem. An excited electron drops from the n equals 7 level to the n equals 4 level. Calculate the wavelength of the electromagnetic radiation emitted as a result of this electronic transition. Here is our Rydberg equation. This is a constant, of course, and now all we have to do is evaluate which is initial and which is final. Well, of course, 7 is initial, so we're going to plug that in here. 4 is final, and we're going to plug that in here. When we solve, we note that we get a very small number, a negative 9.176 times 10 to the negative 20 joule. Now, as noted, we just take the absolute value of this. And when we do, we're going to get, of course, just 9.176 times 10 to the negative 20. We can plug that number in here for our E value. And recall that E equals h times the frequency. However, we want our answer to be wavelength. So if we consider that C equals lambda times wavelength, we can rearrange this equation to solve for frequency. Frequency equals c over lambda, so we can plug c over lambda in for the frequency term here. This gives us E equals Planck's constant times the speed of light over lambda. Since we want to solve for lambda, we rearrange to solve for that, and we get lambda equals Planck's constant times the speed of light over the energy. When we plug the numbers in for this, notice a few things. Joules cancel and seconds cancel. This means we will have an answer in meters. And that answer is 2.17 times 10 to the negative 6 meters. Now, typically, we don't want to be in meters. We want to be in nanometers. So we're going to perform the unit conversion, and we're going to find that our answer of the wavelength for this particular electronic transition, 7 to 4, is 2.17 times 10 to the third nanometers. This is in the far infrared region. Notice that we can see that this transition is 7 to 4. How do we know, apart from looking at this, that it's far infrared? Well, we have to go to an electromagnetic spectrum and look and make sure that our frequency and wavelength are indeed in the far infrared region. So that's all there is to it for this problem. All these problems are very similar. You just need to understand the process of getting from 1 to 2 to 3 and making sure you're careful with your units so that you get the correct answer.